Are we alone in the universe? Does life exist in the solar system other than on Earth? These questions have haunted mankind for centuries. As we explore the outer reaches of our solar system, we're getting closer to the answers every day. From the icy moons of Europa and Enceladus to the vast plains of Mars, evidence is mounting that life may well exist beyond our blue planet. Just imagine hidden oceans teeming with life beneath ice crusts, microbes thriving in the Martian depths, or even exotic life forms floating in the clouds of Venus. The possibilities are as vast as space itself. Dear traveler, welcome. Today we're setting off on an incredible journey to discover the most promising places where life could have developed. But before you set off on your next adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and fasten your seatbelt for immediate takeoff. In their search for extraterrestrial life, astronomers have focused on our two neighbors, Venus and Mars. Not just because they're our neighbors. From our telescopes, we can see some similarities between these planets and our Earth. So you might ask, how does our planet resemble Venus, with its thick clouds of sulfuric acid? Or Mars, with its desolate crater-strewn surface? In fact, these three planets have much more in common than you might think. All three have atmospheres with clouds. We can see distinct zones, which may resemble continents. On Mars, there may even be cyclical seasons like on Earth. At least this is what the changes in the polar cap on Mars show. On this seemingly dead, cold, and arid planet, there would be alternating colder and warmer seasons, just like on Earth. The challenge was to find out what kind of life could inhabit these planets. To go any further, we had to answer another question. What form of life are we looking for? What would life look like on other planets? To answer this question, the scientists took the logical route. They started with life as we know it on Earth. This is the only form of life we know of. We therefore looked for the conditions that favor the development of life on Earth, i.e., its appearance, reproduction, and evolution. On our planet, it's liquid water that has enabled life to develop. It's because liquid water is abundant on Earth that life has been able to emerge and thrive. So we first focused our research on the environments in our solar system where liquid water can exist. Our solar system has one star, the Sun, 8 planets, over 200 satellites or moons, thousands of asteroids, and billions of comets. There's a lot of celestial objects to observe. Is the search for liquid water like looking for a needle in a haystack? No, because for water to remain in a liquid state on a planet, several conditions have to be met. Moderate temperatures, neither too cold nor too hot. Precise atmospheric pressure, between 0.6% and 130,000 times normal atmospheric pressure. An atmosphere as on Earth that blocks the UV rays emitted by the sun, which are harmful to life as we know it. What's more, liquid water is not the only requirement for life to develop. Mineral salts and a source of heat are also needed. With all this in mind, we were able to narrow down the field of possibilities. Let's take a quick look at the planets in our solar system to see which of them are currently home to liquid water. Let's start with Mercury, the least well-known planet. It's the smallest rocky planet, but also the closest to the Sun. Because it has virtually no atmosphere and is so small, temperature variations on this planet are extreme, ranging from -180 degrees Celsius, or -292 degrees Fahrenheit at night, to +430 degrees Celsius, or 806 degrees Fahrenheit, during the day. If Mercury once contained water in a liquid state, that water has certainly evaporated by now. All the more so as its gravity is very weak, too weak to retain liquid water. From a scientific point of view, the explanation is quite simple. Too weak a gravity prevents gaseous water molecules from remaining in Mercury's atmosphere. What's more, Mercury has been geologically dead for over 3 billion years, i.e., it has no internal geological activity. Let's move on to Venus. Venus is a fascinating planet. It's a hellish planet subject to an enormous greenhouse effect. Its atmosphere is 100 times denser than Earth's, and filled with toxic clouds of sulfuric acid, which rain down on the planet. 96% of its atmosphere is carbon dioxide. With temperatures of around 462 degrees Celsius, or 864 degrees Fahrenheit, it's hot enough to melt lead. The pressure on Venus is 90 bars, or 90 times higher than on Earth. In other words, walking on Venus would be as difficult as walking underwater on Earth at a depth of 900 meters, or 3,000 feet. Any living thing that set foot on Venus would be crushed. What's more, Venus is dotted with erupting volcanoes, craters, and lava lakes. As you can see, there can't be any liquid water on Venus. Our neighbor Mars is perhaps the planet in which scientists have placed the most hope. Unlike Venus, Mars lies in the Sun's habitable zone, just like Earth. The search for liquid water on Mars began in the 1970s. Unfortunately, it was not very conclusive. At present, there is no liquid water on the surface of Mars, as its atmospheric pressure is too low. But the planet has certainly contained liquid water in the past. In fact, it still contains water today, but in the form of ice. And because Mars is still geologically active, relatively recent volcanic eruptions may have melted this icy water and caused liquid water to reappear. We'll come back to this later. In the meantime, let's continue our little journey by taking a look at the gas giants of our solar system. It's unlikely that Jupiter or Saturn, which are gas planets rather than telluric planets, are home to liquid water. It's far too cold. The Galileo probe identified water vapor in clouds of water ice on Jupiter. As for Juno, it has calculated that water, or rather its gaseous components reduced to atoms, represent 0.25% of the various gases present in the planet's atmosphere. This represents 3 times the amount of water present in the Sun. But there's a shadow over this picture. These results contradict those of the Galileo probe, which found 10 times less gaseous water in Jupiter's atmosphere in 1996, concluding that it was drier than the Sun. It is also likely that the gas giant's core contains ice. Whatever the case, Jupiter has traces of water, but no traces of liquid water. The same applies to Saturn. There are small quantities of water vapor in its atmosphere, but no liquid water. Let's continue our exploration with the two icy planets, Uranus and Neptune. Here again, the most obvious answer is that no water is found on these planets, or at least not in liquid form. In fact, researchers believe that both planets are made up of water and contain an icy core. Water can be found in 3 forms on Uranus and Neptune: icy, liquid, and superionic. What is superionic water? It's not the same form of water we have on Earth. It has some very strange properties. Denser than our terrestrial water, it carries an electrical charge, as it is made up of several molecules dissociated into positive and negative ions. It is more electrically conductive than water on Earth. Superionic water, subjected to extremely high temperatures and pressures, lies somewhere between the liquid and solid states. You may have gathered that Uranus and Neptune contain liquid water and could therefore harbor some form of life. Perhaps, but it's highly unlikely that this is an advanced form of life like ours. Let's not forget that Uranus and Neptune are gaseous planets. They have no solid surface and therefore no soil. You can't walk on them, let alone land on them. We've completed our tour of the planets in the solar system. The hope of finding a habitable planet with liquid water, an atmosphere, a solid surface, and acceptable temperatures seems slim. But planets aren't the only celestial bodies in our solar system. Scientists are increasingly turning their attention to the satellites of the planets we've just explored: Europa, Titan, Enceladus. All these moons could potentially harbor some form of life. We'll come back to this later. But there's another factor to consider. Since we started looking for liquid water in the solar system, we've broadened our horizons. We are no longer looking for a form of life exactly like that found on Earth, evolving under the same conditions. We are now aware that life can develop in extreme environments. It happens on Earth in the depths of oceanic faults, in the rocks of the Earth's mantle, or in hypersaline environments like the Atacama Desert in Chile. So why can't it happen on other planets? Are lack of water and extreme conditions obstacles to life? Not necessarily. In recent years, a great deal of research has been carried out on environments considered extreme. Geysers, oil wells, volcanoes, ocean faults. Surprise! In all these environments, bacterial life can be found at a minimum. These bacteria are surprisingly resilient. They survive in extreme environments, withstanding heat and high or low pressure. It has long been known that microorganisms can be transported to high altitudes by storms or volcanic eruptions. But it was thought that even if living organisms could be found at very high altitudes, it was impossible for them to survive or even reproduce. At these altitudes, microorganisms are subjected to intense ultraviolet radiation and very low temperatures. not to mention the absence of food. And yet, incredible as it may seem, they managed to survive in such environments. Birgit Sattler, a specialist from the University of Innsbruck, has demonstrated that around 1,500 bacteria survive in droplets of water ice on the Sonnenblick mountain near Salzburg at altitudes of 3,000 meters or 10,000 feet. These bacteria don't just survive, they thrive in this extreme environment, at the speed of plankton. It's only a short step from there to thinking that the dense clouds of Venus could provide shelter for microorganisms, which could survive in droplets of water vapor for months on end. And there are dozens of examples on Earth of living organisms surviving in extreme environments. In 2012, bacteria were discovered in a lake under the Antarctic ice, Lake Vida. These bacteria live in unthinkable conditions, without light or oxygen, with a temperature of -13 degrees Celsius or -9 degrees Fahrenheit, and in an environment 6 times saltier than seawater. This salt lake lies beneath a 20-meter or 66-foot thick layer of ice. No interaction with the outside world is possible, nor is photosynthesis possible, especially since, according to analyses, this underground lake has been isolated for over 2,800 years. And yet, no less than 8 phyla of bacteria have been observed, representing an astonishing diversity of microorganisms. It's a different, non-solar energy source that these bacteria use to survive. In concrete terms, this could involve what are known as serpentinization reactions, an anaerobic oxidation reaction between water and iron ions present in dissolved form in the water as a result of rock erosion. This discovery, together with many others of the same type, opened up our horizons and broadened our perspectives. Scientists are now leaving no stone unturned. Even an underground lake buried under a layer of ice could be a source of life. That's why even the planets least likely to harbor life have been scrutinized. This is what happened on Mercury, the smallest planet and closest to the Sun. We saw at the start of our journey that Mercury can't harbor liquid water because it's too close to the Sun and its temperatures are too high. And yet, strange as it may seem, this little planet is not completely devoid of water. Indirect scientific measurements have shown that some surface water remains at the poles in the form of ice. This water is found at the bottom of craters that are never illuminated by the sun and whose temperature remains around -200 degrees Celsius or -328 degrees Fahrenheit. Even more astonishing, this ice could contain biological elements. How do we know? Scientists at the Planetary Science Institute, PSI, in Arizona, USA, recently discovered traces of biological life on saltwater glaciers on the Earth's surface. So far, so good. Except that these glaciers are subject to extreme climatic conditions and are rich in salt, just like on Mercury. Could it be, then, that these saline compounds create habitable niches in Mercury's craters, as in the Atacama Desert? Perhaps because volatile compounds long thought to be gone have also been found on Mercury: sodium, potassium, sulfur, and chlorine. While it's now certain that extraterrestrials don't live on Mercury, scientists believe it's likely that the craters on this small, hot planet are home to a wealth of microbial life. If there may be life on Mercury, why not on Venus? Venus was once thought to be uninhabitable, but now questions are being asked. As we saw earlier, Venus does not at all offer conditions conducive to life. On the contrary, it seems impossible for life to exist on this hellish planet, swept by sulfuric acid rain, suffocated by a powerful greenhouse effect, and crushed by intense pressure. And yet, until the late 50s, scientists believed that Venus's clouds were made up of water vapor. It was therefore thought that Venus had a tropical climate. After all, our neighbor is the same size as Earth and closer to the Sun than we are. We therefore imagined that Venus's surface was covered with jungles, oceans, and deserts. It was also thought that there was life on Venus, and that it resembled life on Earth during the Carboniferous and Permian periods. Of course, the first analyses of Venus quickly changed the image people had of the planet. But more recently, at the turn of the 21st century, we've been asking ourselves the same question, in a different guise. Scientists wondered whether the thick clouds of Venus might be a refuge for some form of life. This idea was first put forward by the famous planetary scientist Carl Sagan in an article written in 1967 for the prestigious journal Nature. He hypothesized that Venusian clouds could provide a habitable niche for life. This theory was substantially taken up by numerous scientists, who in turn developed scenarios, hypotheses, and models to explain how life could have emerged on Venus and subsisted in its upper atmosphere. Indeed, at 50 kilometers or 31 miles above the surface of Venus, the temperature is milder. Temperatures range from 30 to 80 degrees Celsius. Pressure, meanwhile, is similar to that at sea level on Earth. One of these scientists is German astrobiologist Dirk Schultz-Makuch from the University of Texas at El Paso. In 2002, he resumed analysis of data from the Pioneer probes, the very first probes launched by the USA at the beginning of the space age. These analyses revealed several anomalies. First, there's this mysterious phenomenon in Venus's atmosphere: dark spots caused by something that seems to filter out the sun's UV radiation. Then there's the concentration of carbon monoxide measured by the probes, which is surprisingly low. Hydrogen sulfide was also detected, although it should have been transformed long ago by sulfur dioxide, which would mean that it continues to be produced by something. From these observations, German astrobiologist Dirk Schultz-Makuch concluded that there must be living microorganisms in Venus's atmosphere, consuming sulfur dioxide and carbon monoxide, and secreting hydrogen sulfide. To do this, they would use sunlight, which explains the dark patches seen in Venus's atmosphere. These findings, made in the early 2000s, have been steadily supported by further analysis, leaning in favor of bacterial life in the clouds of Venusian atmosphere. In fact, since the early 2000s, the search for life in the clouds of Venus has been a roller coaster ride of ups and downs, hopes and disappointments. As recently as 2020, a team from Cardiff University in Wales announced that they had detected phosphine in Venus's atmosphere. Phosphine is produced on Earth by living organisms. But this hypothesis, like most hypotheses in favor of life on Venus, has been refuted. In fact, Venus is thought to be the site of active volcanism, producing phosphine. In 2021, a study published in Nature Astronomy was definitive. There is no possible active life in the clouds of Venus. Microbiologist John Halsworth from Queen's University Belfast looked into the matter. He studied the minimum amount of water that the most resistant microbes on Earth need to remain active and thrive. He compared this quantity to the amount of water available in Venus's atmosphere. It's over 100 times too little. In other words, even the most resilient microorganisms known on Earth wouldn't survive in our neighbor's atmosphere due to a lack of water. This brings us back to our original problem. Without liquid water, there's no life. In any case, this research may not have been successful, but it did provide some interesting information about Venus. From now on, scientists will be keeping a close eye on this planet, which apparently has yet to reveal all its secrets. 3 probes will explore Venus around 2030. This will be an opportunity to confirm the data we already have on Venus, particularly in terms of temperature and pressure, but also the amount of water available. And even if Venus is not currently home to any form of life, we can't rule out the possibility that it was once home to a multitude of living beings. It is thought that several billion years ago, Venus was similar to the primitive Earth. Hard to imagine? Yet this hypothesis is widely accepted by the scientific community. This period during which Venus resembled early Earth is thought to have lasted over 3 billion years. According to scientific models, the planet was then covered in liquid water, with stable tectonic plates and pleasant temperatures between 20 and 50 degrees Celsius, or 68 and 122 degrees Fahrenheit. This is bearable for living organisms, as it's close to our own terrestrial temperatures. Venusian oceans were between 10 and 300 meters, or 30 and 300 feet deep. Some of the water was locked up in the planet's soil, as on Earth with our water tables. So, for 3 billion years, Venus may have been habitable. But then what happened? $700 million years ago, something happened to transform Earth's twin into the hellish planet we know today. The most likely hypothesis is that a major geological event occurred. Large quantities of magma boiled over, releasing tons of CO2 into Venus's atmosphere. Whereas on Earth, rocks would absorb most of the CO2 to prevent it from entering the atmosphere in excess, on Venus this did not happen as expected. Magma solidified on the planet's surface. It covered the rocks in a thick, impenetrable layer. In a way, it smothered the rocks. They could no longer absorb the CO2. The same phenomenon occurred on Earth 252 million years ago, leading to a mass extinction, the Permian-Triassic extinction. Nicknamed the Great Death, this mass extinction was the worst of the 5 great extinctions that Earth has known. 252 million years ago, over a period of 60,000 years, 96% of all marine and terrestrial species became extinct. Forests were wiped out. They only regained their former extent 10 million years later. Marine ecosystems took between 4 and 8 million years to recover. The Permian-Triassic extinction is explained by what are known as Siberian traps. The Siberian traps are an intense volcanic complex that spewed over 3 million cubic kilometers of lava across present-day Siberia. the eruption released at least 14,500 billion tons of carbon. That's more than 2.5 times what would be released if every milligram of Earth's fossil fuel were dug up and burned. Impressive, isn't it? And that's not all. Magma from the Siberian traps then seeped into the coal fields towards the surface, releasing even more greenhouse gases like methane. The result was unprecedented global warming. Over the next million years, seawater and soil temperatures rose by several degrees. By 250.5 million years ago, sea temperatures at the equator had reached 40 degrees Celsius, or 104 degrees Fahrenheit. Temperatures continued to rise, altering the rocks. Acid rain sent volcanic sulfur back to Earth. The oceans lost 76% of their oxygen. This is what led to the loss of so many species. What if the same thing had happened on Venus, only worse? On Venus, the atmosphere would have become 90 times denser than on Earth as a result of this event. This enormous greenhouse effect raised the planet's temperature to over 460 degrees Celsius, or 860 degrees Fahrenheit, and solar radiation began to hit its surface. All liquid water disappeared from the surface of Venus. To find out whether or not there was life before this catastrophe, researchers want to understand whether this event happened all at once, or whether there was in fact a series of events spread over several 100 million years. To find out more, we need to send even more probes to Venus. Just like Venus, and perhaps even more so, Mars is of interest to scientists. Our neighbor, the fourth planet in the solar system, could harbor life, or at least have harbored life in the past. As we saw at the start of our journey, Mars has long been of interest to scientists, as it is very similar to Earth. In fact, Martians have invaded fiction at one time. War of the Worlds, The Martian Chronicles, Mission to Mars. So many films and books featuring little green or gray men emerging from flying saucers. But on closer inspection, the two planets are in fact quite different. Mars has a weak atmosphere, composed mainly of carbon dioxide. Temperatures range from minus 120 degrees Celsius to 25 degrees Celsius, or minus 184 degrees Fahrenheit to 77 degrees Fahrenheit. Let's travel together through the history of the search for life on Mars. It all began in the 17th century. That's when the polar caps of Mars were first observed. In the second half of the 18th century, the German astronomer William Herschel proved that they grew and shrank according to seasonal cycles. The first similarity with the Earth had been discovered. Others followed. A day on Mars lasts about as long as a day on Earth. The inclination of Mars' axis of rotation is close to that of Earth's, which explains why the red planet also has seasons. But Martian seasons are longer than those on Earth. At the end of the 19th century, scientists believed that the dark patches observed on the surface of Mars were oceans, and the lighter areas were oceans. This led to a proliferation of theories about life on Mars. But it was soon discovered that these dark and light spots were nothing more than optical illusions, and that Mars contained neither water nor oxygen. Today, we know that Mars is unlikely to harbor life. It's very cold, minus 40 degrees Celsius or minus 40 degrees Fahrenheit on average. its atmospheric pressure is very low. Its atmosphere is very thin. It lets through UV rays, which are harmful to life. The red planet has no magnetosphere to protect it from UV rays. The Martian soil is saturated with oxygenated water. But, as on Venus, it is thought that Mars may have harbored life in the past. $4.5 billion years ago, water seems to have flowed freely on Mars. The climate was much milder then. In fact, the planet had all the right conditions for the appearance and development of life. Perhaps life on Mars appeared at the same time as life on Earth, some 3.8 billion years ago. But then it was single-celled life, which didn't have time to develop before the water on the red planet disappeared. If this theory is true, then traces of these single-celled organisms should be found in the sedimentary layers of Mars, where the ocean floor was more than 3 billion years ago. It's to unravel this mystery that many space exploration missions are focusing on Mars. Mariner 4 was the first probe to fly over the red planet in 1965. Scientists were disappointed when they saw the photographs brought back by this probe. They showed a desolate landscape, an arid planet with no sign of oceans, lakes, or rivers. No sign of life whatsoever. What the photographs also showed was a cratered surface, meaning that all tectonic and meteorological activity on Mars ceased 4 million years ago. Above all, Mariner 4 confirmed that no multicellular living beings could survive on Mars. Since Mariner 4, the search for life on Mars has focused on simple, unicellular organisms such as bacteria. NASA is in possession of some 60 Martian meteorites, which constitute samples from Mars. One of the best known is the Nakhla meteorite, which fell to Earth in Egypt on June 28, 1911. But these samples should be treated with caution, as they may contain organic elements due to terrestrial contamination. That's why Mars missions are still on the agenda. More recent NASA missions have focused on the following question: were there lakes and oceans on Mars in the distant past? Many clues have been found, including traces left by liquid water on the arid, rocky surface of Mars. On February 8, 2023, for example, NASA found traces of waves on Mars. The Curiosity rover was unable to extract samples from these hard rocks, but the search is on. Interesting elements have also been found in the thin Martian atmosphere, such as methane, formaldehyde, and silica. These elements are either evidence of past microorganic life on Mars or of volcanic activity. For the moment, it's impossible to say. There are also geological phenomena identified on Mars that bear no resemblance to anything known on Earth, and which some scientists believe to be evidence of subterranean microorganic life. Dark dune spots were discovered by the Mars Global Surveyor probe in 1998 to 1999. These strange spots appear in the south polar region at the start of the Martian spring thaw, and disappear before the onset of winter. They appear to be linked to Martian geysers. A team of Hungarian researchers has theorized that dark dune spots are colonies of photosynthetic Martian microorganisms living beneath the ice layer. When the sun returns to the pole during the spring thaw, light penetrates the ice, and is synthesized by these microorganisms. This heats up the microorganism's environment, causing pockets of liquid water to form trapped in the ice. This is what creates the dark spots. This hypothesis has not been confirmed. It joins the list of possible clues to single-cell life on Mars. Among the questions scientists are asking about Mars is whether it is terraformed. Terraforming is the process of transforming another planet to make it habitable for humans. The term terraforming first appeared in science fiction in 1942, but is more topical than ever. Could terraforming Mars be possible? Maybe, but it would be a lot of work. We'd need to increase the CO2 concentration in the Martian atmosphere to create a greenhouse effect. This greenhouse effect would not be as harmful as on Earth or Venus. It would help us trap the sun's heat. We could also use chlorofluorocarbons, super greenhouse gases, but we'd still need to generate enough CO2 to warm the atmosphere. But if we succeeded, the greenhouse effect would heat up the ice caps and cause them to melt, amplifying the phenomenon by evaporating the CO2 trapped in the ground. Once the water at the poles has melted, lakes and rivers could reform, perhaps even a shallow ocean. But the atmosphere would be unbreathable, so we'd need to add oxygen-producing microbes to Mars, and primitive plants that could absorb CO2 and release oxygen. But the oxygen produced by plants accumulates only very slowly, so we'd have to wait 100,000 years to produce a breathable, oxygen-rich atmosphere. All this, although theoretically possible, is for the moment unfeasible with our current technology. It's time to continue our journey towards the two gas giants of our solar system, Jupiter and Saturn. Let's start with Jupiter, the largest planet in our solar system. As we saw at the start of our adventure, Jupiter cannot support life. It has no solid surface and is far too cold. But Jupiter has no fewer than 95 natural satellites or moons. And Jupiter's moons are of increasing interest to scientists. Of these 95 moons, 4 were discovered in 1610 by Galileo. They are known as the Galilean satellites. They are Io, Europa, Ganymede, and Callisto. According to researchers, Europa and Ganymede could be home to life. Let's find out why. Europa is the closest of the two Galilean satellites to Jupiter. It is also the first natural satellite on whose surface traces of an underground ocean of liquid water have been found. Indeed, this icy moon could have liquid water beneath its icy crust. How is this possible? Before answering this question, we need to know that for liquid water to exist beneath the ice layer, there needs to be an internal energy source, which generates heat and warms up the water. Now, the Hubble telescope has detected faults on Europa's surface, from which geysers spout up to 200 kilometers, or 125 miles high, an undeniable sign of an energy source. This cryovolcanic activity could be linked to the tidal action asserted by Jupiter on its natural satellite, but also by its orbital resonance with Io and Ganymede. In other words, these gravitational interactions would heat the small moon's underground ocean, keeping the water in a liquid state. Europa is locked in by Jupiter's tides, so it rotates synchronously around the gas giant. Slight variations in its rotation have been observed, providing yet another clue in favor of an underground liquid ocean. Yes, in the past, Europa's crust has moved 70 degrees in relation to its interior, which would be simply impossible without a liquid layer beneath the surface. For the moment, the thickness of the ice layer above Europa's ocean is unknown. The only probe that has flown over Europa is NASA's Galileo. All the data we have on this icy moon comes from this probe. What we do know about Europa is that it is barely smaller than our moon. It consists mainly of silicate rock, with a core probably of iron and nickel, and a crust of water ice. Its thin atmosphere is largely composed of oxygen, formed by the decomposition of icy waters by UV rays. On Europa, it's very cold, minus 183 degrees Celsius, or minus 298 degrees Fahrenheit at the equator, and up to minus 223 degrees Celsius, or minus 370 degrees Fahrenheit at the poles. Another special feature of this satellite of Jupiter is that unlike our moon, it has no craters. In fact, it has the smoothest surface of any celestial object in our solar system. Let's continue our exploration of Europa. The Galileo probe has taken measurements of its magnetic field. This has revealed the presence of an electric current that corresponds in every way to that of an ocean of liquid salt water. So that's where we are with Europe. The rest has been modeled for lack of observation. Researchers believe that Europa's ocean could be 100 kilometers or 60 miles deep, with a volume at least twice that of our oceans on Earth. The oxygen concentration on Europa could be sufficient to sustain single-cell aerobic life in its ocean. It remains to be seen whether living organisms could thrive in this subterranean ocean, enclosed beneath a thick layer of ice with no sunlight. This is the case on Earth, in the most hostile depths of the Arctic Ocean, so why shouldn't it be possible on Europa? The European JUICE probe will help us find out more from 2030, as will NASA's Europa Clipper probe, currently under development. Another of Jupiter's moons is of great interest to scientists, Ganymede. Ganymede is the seventh moon from Jupiter and the third Galilean satellite. It is located around 1 million kilometers or 620,000 miles from Jupiter and orbits the planet in 7 days. It is also the largest Jovian satellite and even the largest in the solar system. It's twice as heavy as our moon. It's almost planet-like, with a diameter 8% larger than Mercury's and 2% larger than Saturn's largest moon, Titan. Ganymede is made up of water ice and silicate rocks. It is the only satellite in our solar system with a liquid metal core and its own magnetosphere. And magnetosphere means protection from the sun's harmful UV rays. But that's not all. Like Europa, Ganymede's rotation is controlled by Jupiter's gravitational tidal effects. Ganymede is in orbital resonance with Europa. While it makes one complete revolution around Jupiter, Europa makes 2. Its atmosphere is thin, containing atomic oxygen, dioxygen, and possibly ozone, all of which bodes well for a potential life form. So, it didn't take long for researchers to take a closer look at this mysterious moon planet. Ganymede was examined by the American probes Pioneer 10 and Galileo in the second half of the 20th century. All the data we have on this moon today comes from the Galileo and Juno probes. Scientists believe that, like Europa, Ganymede has an ocean of ice beneath its surface. So far, nothing very original. It wouldn't be the only one, except that it is also thought that this ocean could contain more water than all the oceans on our planet combined. Continuing our exploration of Ganymede, it appears that its surface is less smooth than that of Europa. 1/3 of its surface is studded with 4-billion-year-old impact craters. The remaining 2/3 are lighter areas where large grooves can be seen. It is thought that this relief may have been caused by tectonic activity, certainly triggered by tidal heating. But these are just suppositions. Ganymede remains a mystery to us. We don't know, for example, whether its ocean is sandwiched between 2 layers of ice, or whether there are several layers of ocean separated by different layers of ice, like a millefeuille of water and ice. But what we do know is that this multi-layered salty ocean beneath the ice crust must be at least 200 kilometers or 125 miles deep. If Ganymede seems to have an interesting profile in our quest for extraterrestrial life, its temperature doesn't work in its favor. The average surface temperature is minus 148 degrees Celsius, or minus 235 degrees Fahrenheit. But don't panic. According to scientists, this is no real obstacle to the possibility of life. Within the moon planet, decay mechanisms are undoubtedly at work, heating the satellite from within. According to researchers' estimates, Ganymede's core has a temperature of nearly 1,400 degrees Celsius, or 2,500 degrees Fahrenheit. For the moment, nothing is certain. All the clues to possible life on Ganymede could be false leads. For example, the presence of molecular oxygen in Ganymede's atmosphere may result from the decomposition of water ice under UV light, and not from a biological process. What is certain, however, is that Ganymede will be explored more intensively in the years to come. Researchers want to know whether this mysterious moon and its internally heated subterranean ocean are home to simple life, or even with a bit of luck, complex life. Jupiter's neighbor Saturn also has natural satellites that could well harbor life. Of its 146 known satellites, 2 are particularly promising. The 2 moons that are the best candidates are Titan and Enceladus. Titan is Saturn's largest moon. It is the second largest moon in the solar system after Ganymede. Titan is of particular interest to scientists, as it is the only known satellite to have a dense atmosphere. Its atmosphere is 98.4% dinitrogen and 1.6% methane and ethane. But its atmosphere isn't just dense, it's extremely dense and opaque. The downside is that it's difficult to study accurately. In fact, Titan's atmosphere is made up of layers of opaque fog that partially block out sunlight. Photographing Titan's surface, according to the Huygens probe team dedicated to observing this satellite, is like photographing an asphalt-covered parking lot at dusk. Like Jupiter's moons, Titan is extremely cold. The temperature of its atmosphere averages minus 180 degrees Celsius or minus 292 degrees Fahrenheit, but can reach minus 200 degrees Celsius or minus 328 degrees Fahrenheit at an altitude of 40 kilometers or 25 miles. Titan's surface pressure is 1.5 times that of the Earth. Like Ganymede, Titan is composed mainly of rock and frozen water. Its surface is young, like that of Europa. It's less smooth than Europa's, with a few mountains and cryovolcanoes, but it's still fairly smooth compared with Ganymede, for example, with few impact craters. Like Earth, Titan has seasons, and methane winds and rains create dune landscapes. During its mission to Titan in the early 2000s, the Huygens probe detected elements of life in the atmosphere of Saturn's largest moon. It also spotted something that looked suspiciously like a lake of water. This was confirmed by subsequent flybys, which found hundreds of such lakes in Titan's north and south poles. Titan has thus become the only known environment other than Earth to feature liquid expanses on its surface. Liquid, really? Not sure, given Titan's surface temperature, averaging minus 180 degrees Celsius or 356 degrees Fahrenheit. To find out, the researchers analyzed the infrared waves reflected by Titan's lakes. It turns out that these lakes are in fact lakes of liquid methane and ethane at very low temperatures. Incredibly, on Titan, methane behaves like water on Earth. It carves valleys, fills lakes, forms clouds, and rains down on the moon. Could methane be the basis for another form of life? Could it enable organic molecules to mix and interact, like water on Earth? Scientists have carried out laboratory simulations of Titan's lakes, but in miniature. All we can do now is wait for the results of this study. In any case, if we succeed in proving that liquid methane can create complex life, it will open up infinite prospects. It will mean that on other planets, other forms of life can exist, without the need for liquid water. Titan is one of our best hopes at the moment. The Saturnian moon is very similar to the primitive Earth, but at a lower temperature, with its liquid expanses and thick atmosphere of dinitrogen. It is therefore highly likely that at least one prebiotic natural environment rich in complex organic chemistry will be found there. This is why other missions to Titan are already being planned. NASA's Dragonfly mission is currently under development. If all goes well, a probe should land on Titan around 2034. Saturn's second most promising moon is Enceladus. Why, you ask, is this little moon of interest to researchers? After all, it's only Saturn's sixth largest moon and 14th in distance from the planet. In fact, Enceladus has some astonishing characteristics. To say the least, it doesn't look like any of Saturn's other moons. Look closely at its shimmering white surface. Enceladus looks different from the planet's other satellites. What's more, the crevices, cracks, and protrusions on the small moon's surface show that there has been, and perhaps still is, complex geological activity on Enceladus. Astonishing for a celestial body of this size, 500 kilometers, or 310 miles in diameter on average. Take a look at these four blue faults running parallel to each other, down towards the moon's south pole. These are known as tiger stripes. These faults are 120 kilometers or 75 miles long and several hundred meters deep. Don't you think they bear a striking resemblance to terrestrial faults? Scientists agree. But that's not all. Data collected by the Cassini probe deepens the mystery. Instead of being colder than the moon's surface as you'd expect, these faults radiate heat. On average, they are 95 degrees Celsius or 203 degrees Fahrenheit warmer than the rest of Enceladus. While observing these strange faults, scientists notice that huge geysers are emerging from them, rising hundreds of kilometers above the moon. As on Europa, it is the friction generated by Saturn's gravitational forces that causes the moon to heat up and the ice to melt. As Enceladus approaches Saturn, it undergoes a torsion that creates internal heating. In fact, it's like twisting a piece of metal. The piece of metal heats up and produces heat. This causes the geysers we've seen. Liquid water is projected into the air at an impressive speed of 2,000 kilometers per hour and freezes on contact with the air temperature. Irrefutable proof that there is water beneath the icy surface of Enceladus. What's more, the Cassini-Huygens mission was able to cross these geysers and analyze them. Elements of life have been found there. So, as on the other moons we've explored, there could be life on Enceladus. But life on Enceladus is very different from life on Earth. On this small Saturnian moon, it has been snowing for over 100 million years. Unlike on Earth, the sky would appear black, with geysers silhouetted against the light, like immense jets of ice falling in a fine white mantle over the planet's surface. Enceladus will be easier to analyze than Mars. There's no need to dig for samples from the sedimentary rocks. All we have to do is cross the geysers and analyze the elements brought to us on a silver platter. The main obstacle is that the rate at which these geysers appear is quite irregular. This is why, for the time being, no mission is planned to explore Enceladus. Research is therefore focused on Titan, Europa, or Ganymede, which will be easier to observe. The moons of Jupiter and Saturn are not the only celestial objects that could potentially harbor microbial life in this region of our solar system. Between Jupiter and Neptune lie objects known as Centaurs. These are small celestial bodies halfway between asteroids and comets, which move in unstable, highly elliptical orbits between Jupiter and Neptune. The largest known Centaur, Chariklo, measures just 250 kilometers, or 160 miles in diameter. Why are these small bodies called Centaurs? Like the creatures of Greek mythology, these celestial objects have a dual nature. In fact, the boundary between comets and asteroids is quite blurred. For a long time, these objects were thought to be asteroids, before being found to have much in common with comets. So much so, in fact, that some Centaurs were thought to be comets temporarily trapped in the orbit of Jupiter or Saturn. In fact, Centaurs have features that remind us of asteroids, but they sometimes outgas, like comets when approaching the inner solar system. For example, Chiron, the first object to be recognized as a Centaur, was discovered in 1977. At the time, it was thought to be a satellite of Saturn or an asteroid. But in 1988, researchers were surprised to discover that it had temporarily developed cometary hair as it approached the perihelion of its orbit. In other words, the point of its orbit closest to the Sun. It was therefore reclassified as a comet, before being considered both an asteroid and a comet, i.e. a Centaur. Researchers believe that some Centaurs may actually be comets trapped in the orbits of the two gas giants. They would then be unable to head towards the Sun. But others are probably minor planets from the outer region of the solar system, the Kuiper belt. Their orbits are then disrupted by the giant planets. Like the Sun, which is a yellow star but will become a red giant before becoming a white dwarf, Centaurs are destined to evolve, and their state is only transitory. All these objects will leave the Centaur family within a few million years at most. Eventually, comets are expected to leave the solar system or collide with the Sun. The number of Centaurs is estimated at just 21. As you can see, Centaurs are rare, so we have fewer opportunities to observe them. No Centaur has yet been imaged by a space probe. That's why these objects are little known. However, it is thought that, like most satellites and asteroids, Centaurs have no atmosphere, as their gravitational field is too weak. On these objects, as on comets, water is abundant, but in the form of ice. In the case of comets, this water sublimates as they pass close to the Sun. Centaurs may therefore carry reservoirs of water, which, like those on the moons of Jupiter and Saturn, could contain microbial life. As we've seen, Centaurs are rare, and few studies have yet been carried out on these small celestial bodies. But there's no doubt about it. If there's even the slightest possibility of microbial life being found on them, scientists will be quick to turn their attention to these mysterious objects in our solar system. We're nearing the end of our journey through the solar system. We still have 2 planets to explore, Uranus and Neptune. These are icy planets like the moons of Jupiter and Saturn we've just seen, but they're also gaseous planets, so scientists don't think they're likely to harbor any form of life. Uranus was only visited by the Voyager 2 probe in 1986, but another probe should be launched towards the 7th planet of the solar system by 2031. Although not thought to harbor life, Uranus is nonetheless intriguing. Composed mainly of hydrogen and helium, but also water, ammonia, and solid methane, it is surrounded by 12 rings and 28 moons. It has a strange magnetic field and seems to lie on its orbit. Its poles are where we have our equator. Uranus is a planet of extremes. It has brilliant clouds, radiant auroras, and violent winds, the most powerful in the solar system after Neptune. It's also the coldest planet in our solar system, despite not being the furthest from the Sun. It boasts freezing temperatures, averaging -195 degrees Celsius or -319 degrees Fahrenheit. Temperatures can drop as low as -224 degrees Celsius or -372 degrees Fahrenheit. No wonder it's so cold. Its core temperature is 4,727 degrees Celsius or 8,500 degrees Fahrenheit, which is quite low compared to Jupiter, for example, whose core temperature is over 20,000 degrees Celsius or 36,000 degrees Fahrenheit. Uranus produces no internal heat, yet another argument against life. As for Neptune, it's the densest planet in the solar system. Like Uranus, it is an ice giant. Its atmosphere contains hydrogen, helium, traces of hydrocarbons, and water, ammonia, and methane. Inside, it contains rocks and ice. As we mentioned earlier, Neptune is the planet with the strongest winds. Its winds can reach 2,100 kilometers per hour, or 1,300 miles per hour. Its temperatures are also particularly icy. They can reach minus 218 degrees Celsius or minus 360 degrees Fahrenheit. So Uranus and Neptune are definitely not candidates for potential life forms. As with Jupiter and Saturn, however, their moons are of interest. One of the most interesting is Triton, the largest of Neptune's 16 moons. Like Europa, Ganymede, Titan, and Enceladus, Triton may conceal an internal ocean. According to estimates, the imposing mass of its core would allow sufficient heat production to maintain an expanse of liquid water between 20 and 140 kilometers, or 12 and 90 miles deep. One of the aims of NASA's Trident mission is to find out more about this mysterious moon, and above all, whether it is habitable. The mission is scheduled for launch on October 25, 2025, with Triton's flyby scheduled for June 28, 2038. The probe will be equipped with all the instruments needed to determine whether the moon hides an underground ocean. This mission will also enable us to glean valuable information from Triton's fumaroles to understand the formation of interior oceans and, more generally, the presence of water in the solar system. Mercury, Venus, Mars, Europa, Ganymede, Titan, Enceladus, the Centaurs, Triton. So many avenues to explore to perhaps one day find a form of life elsewhere than on Earth. While we no longer expect to find an advanced civilization, or at least not in our solar system, we continue to search for traces of a complex form of life that exists or may have existed in the past. Not only will we feel less alone in the vastness of the universe, but we may also learn more about our own origins, or, even more dizzyingly, our own destiny. The Wolf 1061 star system is located 13.8 light-years from our solar system. Between the Earth and Wolf 1061, there is no vacuum, quite the contrary. Space, contrary to what many think, is not empty. There is no air, but there are gases, dust, molecules, and atoms. There are also many celestial objects: stars, exoplanets, satellites, comets, pulsars. There would be about 30 stars between the Earth and Wolf 1061. On our way, we will cross a multitude of stars, some of which are the center of a planetary system. Wolf 1061 is not the closest exoplanet to Earth, but it is one of the few exoplanets that seem most likely to harbor life. We will take advantage of our trip to the Wolf 1061 star system to observe several exoplanets that astronomers have already studied in hopes of finding traces of extraterrestrial life. On our way, we will pass several exoplanets that are already candidates for the title of the closest exoplanet to Earth where life exists. First stop, the Proxima Centauri planetary system. Located 4.2 light-years away in the Centaurus constellation, Proxima Centauri is officially the closest star to the Sun. It is also called Proxima Centauri, Alpha Centauri C, or Alpha Centauri C. Proxima Centauri forms with the stellar pair Alpha Centauri A and B, the Alpha Centauri system. Despite its proximity to Earth, Proxima Centauri is not the brightest star in our sky. That title goes to the star Sirius, located 8.6 light-years from Earth, which is only the fifth closest star system to the Sun. If Proxima Centauri is not that bright, It is because it is a red dwarf. Red dwarfs can be up to 1,000 times less luminous than the Sun. And then, its mass is only 1/8 that of the Sun, which explains why Proxima Centauri is so dim. On August 24, 2016, an exoplanet was detected orbiting this red dwarf star, Proxima Centauri b. This is the closest exoplanet ever found. Proxima Centauri b is a rocky planet like the Earth. This exoplanet is located in the habitable zone of the star, although it is 7.7 times closer to Proxima Centauri than Mercury is to the Sun. This is because Proxima Centauri is a red dwarf. It therefore emits less energy and heat than a yellow dwarf like the Sun, or a white dwarf like Sirius. Its habitability zone, i.e., the zone where water could be found in liquid form thanks to temperatures that are neither too cold nor too hot, is therefore closer than the habitability zone of the Sun, in which the Earth and Mars are located. However, studies conducted on Proxima Centauri b to determine if life would be possible there have not had the expected conclusion. Astronomers note that Proxima Centauri b is 250 times more exposed to X-rays than Earth, which would make life as we know it impossible. And even if the planet had an atmosphere, it would not withstand the repeated onslaught of frequent eruptions from the red dwarf Proxima Centauri. However, even though it is unlikely that life would survive on such a planet, some astronomers remain optimistic. There are so many exoplanets orbiting red dwarfs that it is likely that there are forms of life that we do not suspect are doing very well there. We might be surprised by the adaptability of some life forms. In fact, Lisa Kaltenegger and Jack O'Malley James, two researchers from the Carl Sagan Institute at Cornell University in New York State, have published a paper along these lines in 2019 in the journal Monthly Notices of the Royal Astronomical Society. Their argument is well thought out. The Earth, in its infancy 3.9 billion years ago, endured even worse storms than Proxima b is currently experiencing, and yet life was able to resist and thrive. The researchers compared the characteristics of the atmospheres of Proxima Centauri b and 3 other near-Earth exoplanets to those of Earth. They compared parameters such as atmosphere composition and thickness, and compared these results to those of the Earth's atmosphere over the course of its history. Of course, for these comparisons, models were used, since the atmospheres of these exoplanets have never been directly observed, only deduced via the mass or density of the planets. The results of this study indicate that even if the atmosphere of Proxima Centauri b is eroded and devoid of oxygen, the UV radiation at the surface remains below the levels known by the primitive Earth, including during the eruptions of the red dwarf Proxima Centauri. Conclusion: UV radiation is not a limiting factor for the habitability of rocky planets around red dwarfs. In January 2019, about 3.5 years after the discovery of Proxima Centauri b, a second planet was detected, orbiting the star Proxima Centauri. This planet was named Proxima Centauri c. The existence of this exoplanet is not yet confirmed, but it would be a super-Earth, i.e., an exoplanet with a mass between that of the Earth and that of a giant planet. Its mass would be at least 5.8 times that of the Earth, and its orbital period would be 1,928 days, or a little more than 5 Earth years. Proxima Centauri c could also be a mini Neptune, i.e. a gas dwarf planet with a rocky core and surrounded by a thick atmosphere. Because of its large mass and distance from its star, Proxima c is probably not habitable. Its equilibrium temperature is estimated to be minus 234 degrees Celsius, or minus 389 degrees Fahrenheit. More recently, in February 2022, a team of astronomers using the Very Large Telescope VLT of the European Southern Observatory, ESO in Chile, detected the presence of a third exoplanet around Proxima Centauri. This planet has been named Proxima Centauri d. It would be one of the lightest exoplanets detected to date around a star. The Proxima Centauri planetary system continues to surprise us and to break records. It is not surprising that many teams of astronomers have been studying this stellar system close to our own. The radial velocity technique was used to discover Proxima Centauri d, a very light exoplanet. When a planet orbits its star, it makes it move. This movement modifies the light spectrum that our instruments on Earth capture from this star. An object approaching us is red-shifted, while an object approaching us is blue-shifted. This shift is proof that the star is moving, and that an object is orbiting it. Proxima Centauri d would have a mass equivalent to a quarter of that of the Earth, and it would orbit its star in about 5 days. It is located very close to its star, about 1/10 the distance of Mercury to the Sun. According to the first estimates, it would not be habitable. But this statement should be taken with caution in the absence of information on the presence or absence of an atmosphere that could generate a greenhouse effect. Of the 3 exoplanets discovered around the star Proxima Centauri, Proxima b, the first to be discovered, is the most likely to be inhabited. However, we could not physically go there with our current means of propulsion. Take the example of the New Horizon probe, which travels at a speed of 17 kilometers per second, or 10 miles per second. At this speed, it would take us 78,000 years to reach Proxima b, and yet it is the closest exoplanet to Earth. Astronomers can only imagine what life would be like on this planet if they cannot see it with their own eyes. Like most planets orbiting red dwarfs, it would be in synchronous rotation around its star, and would therefore always present the same face. One could therefore imagine that one side would be immersed in darkness with very cold temperatures, and the other would be constantly exposed to very high temperatures. The liquid water and the life could, on the other hand, develop at the border between these two zones. You will see in the rest of our journey that most exoplanets orbiting a red dwarf are in this configuration because of the tidal effect. Let's continue our journey towards Wolf 1061. Before going further, let's stop at 8.3 light-years from Earth, where the 4th closest exoplanet to our solar system ever detected is located, after the 3 exoplanets of the Proxima Centauri system. This exoplanet has been named GI 411b. It was detected by an international team of astronomers in 2019 at the Hot Province Observatory, thanks to the SOFI spectrograph installed on the observatory's 1.9-meter or 6 feet telescope. The telescope of the Observatory des Hautes Provinces is the one which allowed the discovery of the very first exoplanet in 1995, 51 Pegasi b. For the record, 51 Pegasi b orbits a yellow subgiant, a class of stars brighter than yellow dwarfs but less than yellow giants. It is located 51 light-years from us. At the time, no exoplanet closer to Earth had been discovered. This is not the only record that was broken by 51 Pegasi b. Astronomers also had to create a new type of planets to characterize it, because until then, no gas giant as close to its star had been discovered. 51 Pegasi b is therefore what is called a hot Jupiter. Let's go back to the fourth closest exoplanet to our solar system, GI 411b. In 2019, when it was discovered, GI 411b was the third closest known exoplanet to Earth. But it has since been dethroned by Proxima Centauri d, discovered in 2022. The mass of GI 411b is equivalent to 3 times that of the Earth. It orbits the star GI 411 in the Big Dipper constellation in 13 days and is probably rocky. It is very close to its star, only 0.08 astronomical units away, about 5 times closer than Mercury to the Sun. To discover the exoplanet GI 411b, astronomers looked at the observation of red dwarfs. It is easier to find an exoplanet around a red dwarf. First, because these stars represent 80% of the stars in our galaxy. Second, because their mass, much smaller than that of the Sun, makes them more sensitive to the gravitational influence of the planets orbiting around them, which makes them more easily detectable. This is how the SOFI spectrograph detected the exoplanet GI 411b. By detecting the motions caused by the planet's mass on its star as it orbits the red dwarf. The observations gathered on GI 411b do not lean in favor of a possible life on the surface of the exoplanet. It is very close to its star, and even though red dwarfs are cooler than yellow dwarfs, it is still too close to be in the habitable zone of GI 411. It could be that this rocky planet is more like Venus than Earth. GI 411b is not a novelty for the Hot Province Observatory, which has already detected nearly 200 planets. But it is very interesting because of its proximity to our solar system. The observation of this planet in the years to come, and especially of its atmosphere, will be crucial for the astronomers, who will be able to compare their observations with the characteristics of the planets of the solar system. Thanks to its proximity to the Earth, GI 411b, like the planets of the Proxima Centauri system, can be observed directly. Let's continue our journey in the universe to discover the closest exoplanets to Earth. Not far from GI 411b is the exoplanet Ross 128b, located 11 light-years from our planet. Discovered in 2017, the exoplanet Ross 128b orbits a red dwarf, Ross 128, and was detected with the HARP spectrograph at the La Silla Observatory in Chile. It is the closest exoplanet to Earth that could potentially be inhabited, because the star Ross 168 is a rather quiet red dwarf. Its eruptions are less frequent and less violent than those of other red dwarfs, which would increase the chances of preserving the atmosphere of Ross 128b if it had one. If Ross 128b contained liquid water, it would be much more favorable to the development of life than Proxima Centauri b, which is constantly bombarded by harmful X-rays and ultraviolet radiation. Although the exact mass of Ross 128b is not known, nor its radius, astronomers have deduced that it has a low mass and is therefore probably rocky with a solid surface like the Earth. To complete these assumptions, there are models that can give us hypothetical information about this exoplanet. According to the models, Ross 128b would probably have a mass 35% greater than that of the Earth, and its radius would be 10% greater. It would receive only 38% more light than our planet, and its equilibrium temperature would be rather stable, between minus 60 degrees Celsius and plus 20 degrees Celsius, or between minus 76 degrees Fahrenheit and plus 68 degrees Fahrenheit. Its rotation period would be about 9.9 Earth days, and its rotation would be synchronous. It would orbit 20 times closer to its star than the Earth to the Sun, about 7.4 million kilometers or 4.6 million miles from its star. It is not yet known if it is located in the habitable zone of its star, because everything depends on its characteristics, in particular, on the composition and thickness of its atmosphere. It would most likely be located at the edge of the habitable zone, but nothing is confirmed yet. According to calculations, Ross 128b has a similarity index with the Earth of 0.86, which makes it the third exoplanet with the highest similarity index. The planet with the highest Earth similarity index is TRAPPIST-1b, with an ESI of 0.90, and the second planet is Kepler-438b, with an index of 0.88. But both of these planets are farther away from us, which makes Ross 128b particularly interesting for astronomers. TRAPPIST-1b remains relatively close, but is still 40 light-years away. As for Kepler-438b, it is very distant, about 475 light-years from our solar system. It is difficult at this time to study the characteristics of the atmosphere of Ross 128b because it does not transit in front of its star. To learn more about this candidate for extraterrestrial life relatively close to us, we must wait for the launch of larger telescopes, such as the ELT, the Extremely Large Telescope, built by ESO, and still under construction in the Atacama Desert in Chile. The ELT, but also the James Webb, will be able to analyze the composition of its atmosphere without using the transits method. On the other hand, here is a piece of information that should give you chills. If Ross 128b was inhabited by an advanced extraterrestrial civilization, then it could have observed the Earth in transit in front of the Sun. Potential aliens from Ross 128b know that we are here and have even had time to determine the characteristics of our planet and its atmosphere. Enough to give you a chill. Let's continue our journey into the heart of the universe in search of the closest habitable planets to Earth. YZ Ceti is a multi-planetary system located 12 light-years from Earth, just next to Ross 128b, as seen from Earth. The particularity of this star system is that scientists have discovered 3 Earth-like exoplanets. It is the second closest multi-planetary system to us, after the Proxima Centauri system. YZ Ceti is a red dwarf in the constellation Whale, which cannot be seen with the naked eye from Earth despite its relative proximity. Its mass is 13% that of the Sun, and its radius is 17% that of our star. It is an eruptive or variable star, which means that it undergoes fluctuations in brightness. In other words, its brightness can increase briefly and suddenly due to flares or stellar spots that move as the star rotates. On August 10th, 2017, was announced the discovery of 3 Earth-like exoplanets around the star YZ Ceti. it is also possible that there is a fourth planet. It would then be one of the smallest planets ever discovered. All 3 planets are too close to the star to be in its habitable zone, but they are all similar in size to Earth. According to astronomers' estimates, they would not exceed 1.5 times the size of the Earth. YZ Ceti b is the closest planet to the star. It goes around it in less than 2 days. It is very close to YZ Ceti, only 0.016 astronomical units from its star. For comparison, 1 astronomical unit is the distance between the Earth and the Sun. It is also the least massive of the 3 exoplanets in this multiplanetary system, with a mass of 0.75 times that of the Earth. YZ Ceti c is located 0.021 astronomical units of the star, and it makes the turn in 3.06 days. Its mass is 98% that of the Earth. Finally, the most distant planet from the star among the 3 exoplanets is YZ Ceti d. It is separated from its star by 0.028 astronomical units, and it goes around in 4.66 days. Its mass is estimated at 1.14 times that of the Earth. The 3 exoplanets of the YZ Ceti system were detected by radial velocity with a HARP spectrograph at the La Silla Observatory in Chile, like Ross 128b. It is not yet known if they can be observed from Earth with a transit method. Their observation would be interesting for astronomers to continue to understand the formation of planets. But unfortunately, there is little chance that these exoplanets, very close to their star, are inhabited. Not far from YZ Ceti on the scale of the universe, you can see the exoplanet Luyten b, 3rd planet with the highest similarity index to the Earth, ex Aquio, with Ross 128b. We are 12.2 light-years from Earth. This planet is also called GJ 273b. It is in orbit around a red dwarf, the star of Luyten, and it is a telluric planet. It was discovered at the same time as another planet, which also orbits the star of Luyten, Luyten c. But it is Luyten b that interests astronomers because it falls into the category of super-Earths. Its mass is equivalent to almost 3 times that of the Earth, and it receives only 6% more sunlight than the Earth. It could therefore be habitable. This is what the non-profit organization METI has sought to verify. The acronym METI stands for Messaging Extraterrestrial Intelligence, which could be translated as sending a message to an extraterrestrial intelligence. And indeed, that is the goal of this organization, to seek ways to communicate with extraterrestrials and send them messages in hopes of one day getting a response. In October 2017, the METI organization sent a message to Luyten b in hopes of making contact with a potential extraterrestrial civilization. These, if they receive and understand our message, could respond by 2042. The message that has been sent is at the same time musical, mathematical, and scientific, and it is coded in radio waves to maximize its chances of being understood by an advanced extraterrestrial civilization. The METI organization was contacted by the Sonar Festival of Barcelona, a music and technology festival, to develop a message that would be sent into the cosmos to celebrate the 25th anniversary of the festival. the signal was named Sonar Calling GJ273b. It was sent from the EXTRATERRESTRIAL transmitter in Tromsø, Norway, over 3 successive days in October 2017. Among other things, it contains a tutorial on basic math and science, explaining physical concepts specific to our civilization, such as radio frequencies or our conception of time. In a way, a practical manual so that the aliens can understand the musical message and respond to us with the same communication process. In addition to the tutorial, the message includes 6 original pieces of music, commissioned by the Sonar Festival, short 10-second pieces of music. You may wonder why the Sonar Festival chose the planet Luyten b, and not, for example, Proxima b, whose habitability is still in question, and which is closer to us. Simply because the star of Luyten is visible from the northern hemisphere, where the transmitter is located. It is therefore more convenient to communicate effectively with potential extraterrestrials. We have now arrived at our destination, about 14 light-years from Earth. You are looking at the Wolf 1061 star system. Before we continue our exploration of the nearest habitable exoplanets to Earth, you need to understand why astronomers are looking for alien life on these exoplanets, and how they go about determining whether or not a particular exoplanet might harbor life. Why are we looking for life on exoplanets when it is very likely that we will never be able to communicate with the life forms that will have been discovered? You may be asking yourself this question, which is quite sensible, because even if a giant telescope allows us to find life on an exoplanet located several tens of light-years away, several things could prevent us from entering into communication with this life. These are the same reasons that are given in response to the Fermi paradox, the paradox that wonders why, if there is life elsewhere than on Earth, extraterrestrials have never manifested themselves. First of all, it is possible that this life is microbial, aquatic, or animal, and that it does not understand us. And even if an advanced extraterrestrial civilization is found, its communication processes will be so different from ours that communication may be impossible. It is also possible that intelligent civilizations have existed, but that they did not last long on the scale of the universe. They would have quickly self-destructed because of technology, a nuclear war, or other. Or they have already tried to communicate with us, but we did not understand their signs, because their communication techniques are still too advanced for us. We can imagine dozens of answers to the Fermi paradox. But all we know is that the presence of extraterrestrial life elsewhere in the universe is not yet certain, and that perhaps the Earth is an exception. We also know that if another form of life is found elsewhere in the universe, it is very unlikely to come across another civilization that is as advanced as ours. So why are we looking for life on exoplanets? Not only to make contact with extraterrestrials, but also to better understand the appearance of life on Earth, and to find out if Earth is an exception. Currently, the Earth is an exception in the universe because it is the only known planet that hosts life. But perhaps our place in the universe is not so exceptional. Scientists are also interested in the question of whether life could exist in other forms. The life we know is based on 6 atoms: hydrogen, oxygen, carbon, potassium, nitrogen, and phosphorus. We have not yet observed other types of life, but that does not mean it is unlikely. This is the subject of exobiology, a discipline that imagines what living things based on elements different from ours might look like, using notions of astrophysics, planetology, biology, and chemistry. To find life on exoplanets, astrophysicists will proceed step by step. First, the idea is to detect an exoplanet by the transit method, or by radial velocity. The transit method is the most used method to detect exoplanets, but it has some limitations. The exoplanet HD 209458b, located 159 light-years away, was the first exoplanet to be discovered with this method. When a planet passes in front of its star, which is called transit, we observe a decrease in the luminosity of the star. This decrease in brightness of a few percent is measurable by photometry. The transit method allows us to deduce certain characteristics of an exoplanet, its period of revolution, its radius, and even, with precise instruments like the James Webb, certain elements present in its atmosphere. But this method has its limits. The planet must pass in front of its star to be detected, an event that is actually quite rare on the scale of the universe. For example, to see Venus pass in front of the Sun, we would have to wait a century. Once astronomers have detected an exoplanet, whatever the method used, they will deduce its characteristics to be able to establish if the planet is in the habitability zone of its star. This is called Goldilocks. The goal is to know if the planet can contain water in a liquid state, which is essential for the development of life as we know it. A planet too close to its star would be too hot, and the water would evaporate, and conversely, a planet too far from its star would be too cold, and the water would freeze. The balance is tenuous. You now understand why, while more than 5,000 exoplanets have been discovered to date, scientists are not yet certain that other forms of life exist elsewhere than on Earth. But being in the habitability zone of its star does not necessarily make the planet habitable. We have a good example in our solar system with Venus, often called the twin sister of the Earth. Astronomers say that until 715 million years ago, Venus was quite habitable, with large oceans like on the primitive Earth. In fact, Venus is very similar to Earth, with a similar mass and size, so it makes sense that they would have been similar in their early existence. But today, Venus is uninhabitable, with an average surface temperature of about 450 degrees Celsius, or 842 degrees Fahrenheit, and sulfuric acid rain. 715 million years ago, something caused a massive injection of carbon dioxide into Venus's atmosphere, creating an uncontrolled greenhouse effect that has resulted in the planet's hellish environment today. The profile of a habitable planet would therefore finally be quite similar to that of Earth, a rocky planet with an atmosphere, neither too small nor too massive. These characteristics are modulated according to the type of star and the distance between the star and the planet. To confirm whether a planet is habitable or not, astrophysicists will not rely solely on its distance from its star or its surface temperature. They will look for biosignatures, in particular, photosynthetic biosignatures, which the largest telescopes today can detect. Now that you know how astrophysicists determine whether or not an exoplanet is habitable, and why they are constantly searching for an Earth-like habitable planet, we can begin to explore the Wolf 1061 system and its planet, Wolf 1061c. The Wolf 1061 star system is organized around the red dwarf, Wolf 1061, located about 14 light-years from us in the zodiacal constellation of Serpentarius. This star is also known as HIP 80824 and V2306 Ophiuchi. For the record, red dwarfs have the ability to burn up to 400 to 500 billion years, 40 to 50 times longer than our Sun. Around this red dwarf orbits at least 3 telluric planets. Wolf 1061c is the one we are interested in today because it is classified as a super-Earth and is located in the habitable zone of the star Wolf 1061. The star Wolf 1061 was first catalogued in 1919 by the German astronomer Max Wolf. This astronomer had published a list of faint stars that had a high proper motion. The proper motion is the apparent motion of the stars on the sky, as seen from the Earth. Later, the star Wolf 1061 attracted the interest of astronomers for its relative proximity to the Earth. Using the radial velocity method, astronomers discovered a triple planetary system consisting of 3 planets, Wolf 1061, B, C, and D. The habitable zone of the star Wolf 1061 is estimated to be between 0.1 and 0.2 astronomical units from the star. The planetary system of Wolf 1061 consists of 3 known planets. It is not excluded that there are others. These planets were detected by analyzing 10 years of observations of the Wolf 1061 system by the HARP spectrograph at the La Silla Observatory in Chile. The team of astronomers behind the discovery used radial velocity measurements of the star's spectrum to highlight these 3 exoplanets and their orbital periods. Wolf 1061b orbits the star in only 5 days, while Wolf 1061c takes 17.9 days to circle the star, and Wolf 1061d, further out, orbits in 217 days. The mass of Wolf 1061c is estimated to be at least 4.3 times that of the Earth, making it a super-Earth. The mass of Wolf 1061b is closer to that of the Earth because it is estimated to be at least 1.4 times that of the Earth, while the most distant planet is 5.2 times the mass of our planet. The 3 exoplanets of the Wolf 1061 system have masses low enough to be rocky planets, but this remains a supposition since we know neither their size nor their density. If this were the case, they would probably have a solid surface. To be able to determine these characteristics and to know more about the planets of Wolf 1061, it would be necessary to use the transit method. Even if for the moment no transit has been observed from Earth, astronomers do not give up hope of seeing a transit because the 3 exoplanets have short orbital periods. The chances of seeing a transit are 14% for planet B, 6% for planet C, and 3% for planet D, according to the team of astronomers from the University of New South Wales in Australia. Of the 3 exoplanets in Wolf 1061, only planet C is considered potentially habitable. Wolf 1061b is too close to its star, and Wolf 1061d is located at the outer limit of the habitable zone. Its habitability remains probable because everything depends on its own characteristics, which could not be observed. But while waiting to know more, it is the middle planet, Wolf 1061c, that interests astronomers. Wolf 1061c has long been considered the closest potentially habitable exoplanet. After the discovery of exoplanets closer to our solar system, it is part of the growing list of the closest potentially habitable exoplanets, along with Proxima Centauri b, Ross 128b, and Luyten b. It is, after Proxima Centauri b, the second potentially habitable planet in a triple planetary system. Wolf 1061c is a super-Earth located near the inner limit of the habitable zone of Wolf 1061. The habitable zone of the red dwarf has been estimated by astronomers to be between 0.11 and 0.21 astronomical units, or at most between 0.09 and 0.23 astronomical units. Wolf 1061c is located at 0.08 astronomical units from its star, thus at the lower limit of the habitable zone. It is called a super-Earth because its radius has been estimated to be more than 1.5 times that of the Earth. Its mass is 4.3 times that of the Earth, and its surface gravity is estimated to be 1.6 times that of the Earth. All these estimates have allowed astronomers to assume that Wolf 1061d should have a density close to or greater than that of the Earth. Other characteristics of Wolf 1061c could be estimated from the astronomers' observations. Its orbital period is 17.9 Earth days, and its equilibrium temperature is about -50 degrees Celsius or -58 degrees Fahrenheit, slightly higher than the equilibrium temperature of Mars. Wolf 1061c receives less than 1% of the Sun's luminosity. All these characteristics are only guesses at the moment, because the observation of Wolf 1061c was made with the radial velocity method. To know more, and to confirm the estimates of the astrophysicists, it would be necessary to observe a planetary transit. The method of transits would give us a more certain estimate of the radius, and thus of the density of the planet. We could then know if Wolf 1061c is an ocean planet or not. Because it is very close to its star, Wolf 1061c is certainly in synchronous rotation. As we saw at the beginning of this journey with the exoplanet Proxima Centauri b, it is indeed very likely that there is a tidal effect that makes the planet turn on its axis at each revolution around the star. This tidal effect would be explained by its proximity to its star, Wolf 1061. The planet Wolf 1061c would therefore always present the same face to its star, and could therefore harbor life only in the zone of separation between the diurnal face and the nocturnal face. This fictitious line between the illuminated zone and the zone perpetually plunged into darkness is called terminator. Unless the atmosphere of Wolf 1061c is thick enough for there to be a heat transfer from the day hemisphere to the night hemisphere. If Wolf 1061c were in our solar system, it would be too hot to harbor life because of its proximity to its star. But Wolf 1061, which is a red dwarf, is much cooler than our Sun. For comparison, its surface temperature is about 3,030 degrees Celsius, or 5,480 degrees Fahrenheit, while the surface temperature of our Sun is around 5,530 degrees Celsius, or 10,000 degrees Fahrenheit. Wolf 1061c is therefore well and truly in the habitable zone of its solar system. But to know if Wolf 1061c harbors life, it would be necessary to study its atmosphere. Being in the habitable zone is not enough for life to develop on a planet. As we have seen, the example of Venus is enough to understand that a planet can be rocky like Earth and located in the habitable zone of its star, but have characteristics that make life impossible. Astronomers have estimated that life could have developed on Venus for about 3 billion years because the planet's climate was then stable and temperate like Earth's, between 20 and 50 degrees Celsius, or 68 and 122 degrees Fahrenheit. But about 700 to 750 million years ago, a cataclysmic event caused a massive release of carbon dioxide into Venus's atmosphere, a gas that had previously been trapped in the planet's rocks. Some researchers believe that this event resulted from the strong volcanic activity of Venus. The result? An intense greenhouse effect and rising temperatures that have reshaped 80% of Venus's surface. Today, the planet that was considered as the twin planet of the Earth has an average surface temperature of 450 degrees Celsius, or 842 degrees Fahrenheit, and is considered as the hottest planet in our solar system. Venus was the victim of a runaway greenhouse effect. Heat became trapped in the atmosphere, and the planet became too hot for any form of life. Researchers estimate that during the 3 billion years that the planet was habitable, its landscape strongly resembled those of the primitive Earth, with lakes and oceans. These oceans eventually evaporated because of the heat, which only increased the surface temperature of Venus, since water vapor is a real heat trap. A vicious circle that has shaped the planet we know today, often referred to as an iron planet. In the same way as Venus, if the atmosphere of Wolf 1061c is rich in greenhouse gases, it could be too hot for it to be habitable, even if it is rocky, with characteristics close to those of the Earth, and is located in the habitable zone of its star. Stephen Kane, an astronomer specializing in exoplanets at San Francisco State University, and his team have studied the question of the habitability of Wolf 1061c. According to them, the climate of this exoplanet is rather chaotic. On Earth, climatic changes occur at a rather slow pace, since the Earth's orbit lasts 365 days. But on Wolf 1061c, which orbits its star in only 18 days, these climatic variations would be much faster. The frequency of freezing or warming would therefore be very fast. Imagine living on a planet where it is successively very hot and very cold, without transition. That said, astronomers are still waiting for more data on the planet's atmosphere to be able to make a statement. It is possible that the very short periods of freezing are sufficient to cool the planet, but it would be necessary to push the observations even further to confirm one of these hypotheses. Moreover, according to Stephen Kane and his team, because it is located very close to its star, it would be quite possible that Wolf 1061c, like Venus, experiences an uncontrolled greenhouse effect. There is, however, another argument in favor of the planet's habitability. Like Ross 128, the star Wolf 1061 is particularly quiet for a red dwarf. Most red dwarfs are very active and are prone to superflares that would destroy any life on nearby planets. Especially since red dwarfs are cooler than yellow dwarfs like our Sun, planets orbiting red dwarfs are located much closer to their star than the planets in our solar system. Scientists are not yet sure that Wolf 1061c harbors life. We have too little information to say with certainty that this exoplanet relatively close to our Earth is a paradise, a hell, or something in between. Let's assume that Wolf 1061c is potentially habitable. So what would life be like on this exoplanet, 14 light-years away from our solar system? Many researchers claim that humans could not live on this planet. It's true that planets within a star's famous habitability zone are likely to contain liquid water, one of the prerequisites for the development of an advanced civilization like ours. But researchers believe that in the case of Wolf 1061c, the development of life similar to the one we know would be very complicated. The living conditions for humans would not be pleasant, with a gravity 1.6 times greater than that of the Earth. In addition, its synchronous rotation implies that there is a side of the planet perpetually plunged in the dark, with very low temperatures, and another side without ever nights, with very high temperatures. Humans might be able to survive in the middle zone, the Terminator, but they would not live comfortably there. And it is unlikely that in these conditions a species similar to ours, the result of evolution and adaptation to our terrestrial environment, would have been born. But this does not exclude other types of animal or plant species. The question that also arises is that of the conditions of life on a planet orbiting a red dwarf. The synchronous rotation and its two opposite hemispheres are not the only obstacles to the development of a species, such as man on the planet Wolf 1061c. Living next to a red dwarf is not easy. These stars are known for their frequent eruptions, which emit UV and X-rays, dangerous for human life, and for that matter for all forms of life. The surroundings of a red dwarf star are therefore not a very hospitable environment. Yellow dwarfs like our Sun can have outbursts of anger, like red dwarfs. But in addition to being less frequent, they are less dangerous because the planets orbiting a yellow dwarf are more distant than those orbiting a red dwarf. The Earth is far enough from the Sun not to fear possible eruptions, and we are protected by the magnetic field and by our atmosphere. Planets orbiting red dwarfs are too close, and even if they have an atmosphere, it can be torn apart by the onslaught of stellar flares. Scientists believe that there is a cumulative effect. That is, the more flares there are, the more the atmosphere is torn apart, regardless of the violence of the flares. So yes, recent studies have found that red dwarf eruptions are not as energetic as has been thought for years. Researchers may have overestimated the violence of red dwarf flares, but if the cumulative effect exists, it is the frequency and not the violence of the eruptions that is dangerous. However, not all astronomers are pessimistic about the possibility of life developing in the orbit of a red dwarf. Red dwarfs represent 3/4 of the stars in the Milky Way, and we have already discovered many that are surrounded by rocky Earth-like planets. What would be strange is that among all these planets, which are so many possibilities for the emergence of life, there is not a single form of life that is developed. Other factors may affect the habitability of a planet located near a red dwarf. The characteristics of its atmosphere, its thickness, its liquid water content, the interactions between the magnetosphere and the ionosphere with stellar winds. If the right factors are present, an exoplanet of a planetary system organized around a red dwarf could be habitable by creatures other than humans who would resist other conditions. Moreover, the case of Wolf 1061c is promising, since Wolf 1061 remains a rather quiet red dwarf, with relatively low power and infrequent eruptions. Suppose there were life on the planet Wolf 1061c. The conditions for life would be very different from those on Earth. Imagine a world where there are only days or only nights, depending on where you are. The years would also be shorter, since Wolf 1061c orbits around its star in only 18 days. A year would last barely 3 Earth weeks. Because Wolf 1061c orbits a red dwarf and not, like the Earth, a yellow dwarf, the landscapes would also be very different, as well as the luminosity of the planet. Our Sun emits yellow radiation, but red dwarfs emit a reddish radiation. The inhabitants of Wolf 1061c would still have a red star above their heads, and the stellar disk would be larger than that of the Sun, since the red dwarf is closer to Wolf 1061c than the Sun is to the Earth. It is possible that there are plants on Wolf 1061c because plants have a photoreceptor for red light, phytochrome, a blue-green pigment found in plant cells. However, the plants on Wolf 1061c would be very different from terrestrial plants, whether in terms of flavor, smell, or appearance. They would probably be black to better absorb the red light emitted by the star. You may find it difficult to imagine a flourishing life but limited to a small strip in the middle of the planet. This is normal. This representation is very far from what we know. But the good news is that if there is life on Wolf 1061c, it is not necessarily limited to the Terminator if the atmosphere has the right characteristics. For a very long time, astronomers believed that life on synchronously rotating planets was only possible in the Terminator zone. They also thought that for heat transfer to be efficient enough from the day side to the night side, the atmosphere would have to be so thick that it would prevent photosynthesis. It was also thought that such planets would experience high winds and torrential rains all the time, making any complex life forms unlikely. Here is what life looked like according to these assumptions. There are no humans, but plants can survive in such an environment. They can adapt to the constant winds, for example, by anchoring themselves in the ground with their roots, or by developing flexible and unbreakable leaves and branches. There are also animals which communicate by infrared rather than by cries and smells as on Earth, because storms make this type of communication impossible. Underwater life is protected from strong winds and eruptions by the water, and is supported by vast blooms of plankton and black photosynthetic algae. A plankton bloom is when phytoplankton multiply in an ocean. On Earth, this phenomenon has been demonstrated in the depths of the Arctic Ocean and under the sea ice in Antarctica. We can see it forming like a green sheet from space. This phenomenon can only occur if 2 elements are combined: nutrients and light from the star. We can therefore imagine that these forms of underwater life would develop in the oceans of the illuminated hemisphere of Wolf 1061c. Further studies were conducted from the late 20th century onwards with promising results. Astronomers are now a bit more optimistic about the emergence of life on this type of exoplanet. Studies conducted at the end of the 1990s by NASA researchers have shown that the atmosphere of a planet, if it does contain the greenhouse gases CO2 and H2O, only needs 100 millibars, or 10% of the Earth's atmosphere, for the heat of the star to be transported to the night side. This figure is reassuring because it shows that photosynthesis could then take place. Other studies have shown that in the night side, seawater can circulate efficiently without freezing if the ocean basins are deep enough for the water to circulate under the ice cap. In other words, one could very well find underwater life in a synchronously rotating ocean world, even on the night side. A 2010 study estimated that ocean temperatures would not fall below -33 degrees Celsius or -27 degrees Fahrenheit in the hemisphere perpetually immersed in night. For the difference between the day and night side to be minimal, there would have to be clouds. If Wolf 1061c has clouds, then astronomers agree that this greatly increases its chances of being habitable. Wolf 1061c could be an ocean planet. Maybe you have a hard time picturing what this type of planet looks like. Scientists describe them as a planet that would be covered with an ocean or water over its entire surface. The depth of this ocean could be several tens of kilometers, but this type of planet remains hypothetical. For the moment, we can only think about the hypothesis according to which Wolf 1061c would be entirely covered with water without really any evidence to confirm or deny this hypothesis. If Wolf 1061c were an ocean planet, it would be covered with high-pressure and high-temperature oceans. To date, astronomers do not know if this environment would be conducive to biological chemistry. What we do know is that if the oceans of Wolf 1061c were to support life, it would certainly be different from the underwater life found in our terrestrial oceans. We know that the oceans are capable of wonders. The origin of life on Earth remains mysterious, but the most likely hypotheses agree that it was born in our oceans, or at least in water. Underwater life can survive extreme conditions. On Earth, we have found living organisms capable of developing in the Dead Sea. The tardigrade is the best example of an ultra-hardy species that can survive incredible pressure conditions. This 8-legged animal, which can grow to just over 1 millimeter, can withstand temperatures ranging from -273 degrees Celsius or -460 degrees Fahrenheit to +150 degrees Celsius or 300 degrees Fahrenheit, but also X-rays, to which it is 1,100 times more resistant than humans, and pressures 4 times greater than those of the deepest ocean. It can also resist to the lack of oxygen or to the isolation because it reproduces alone. It is cryptobiosis that allows it to be so resistant, a state in which it reduces its metabolic process to 0.01% of normal, so that it is almost dead but not quite. It can remain in this state for decades and rehydrate to wake up at any time. It is therefore quite possible that living organisms of this type can be found on planets like Wolf 1061c, where conditions are less mild than on Earth. There is still much to discover about the secrets of the exoplanet Wolf 1061c. There are many rocky planets in our galaxy, but some of them are located tens or hundreds of light years away from us. Wolf 1061c is one of the most promising because it is close to Earth. The next step to establish an ever more precise portrait of this promising exoplanet is to observe its transit. The transit method will provide crucial information to better understand this planet and determine if it may contain life. When Wolf 1061c passes in front of its star, it will cause a decrease in brightness at Wolf 1061. Scientists will then be able to analyze this difference in brightness to deduce the composition of its atmosphere. The higher the orbital period of an exoplanet, the more difficult it is to apply the transit method, because transits are rarer. In the case of Wolf 1061c, the orbital period is short, which suggests that a transit will be observed rather quickly. Moreover, when the transit method is applied to discover an exoplanet, it is necessary to have observed several transits to conclude that there is a planet in orbit around the observed star. The transit method provides information such as the radius and density of the exoplanet. Astronomers know the spectrum of the star, so they can derive the value of its radius. The relative decrease in the luminosity of the star during the transit is equal to the square of the ratio of the radius of the exoplanet to that of its star. This calculation allows to obtain the radius of the exoplanet. By confronting the radius to the mass, we then deduce the average density. The transit method also provides information on the chemical composition of the planet's atmosphere, as well as its temperature. To do this, astrophysicists measure the spectrum of the star without transit, then with, to deduce the spectrum of the exoplanet. The James Webb Telescope, which was launched in December 2021, will greatly help scientists learn more about Wolf 1061c, its unique characteristics, and whether or not it harbors life. The Space Telescope carries several instruments that allow it to see in the near and mid-infrared. Moreover, in August 2022, the scientific community announced that James Webb had detected the presence of CO2 in the atmosphere of an exoplanet for the first time. This exoplanet is WASP-39b, a gas giant the size of Saturn. It was one of the first exoplanets examined by James Webb from July 2022, and there is no doubt that Wolf 1061c is on the waiting list. Even more impressive, the telescope was able to detect, in addition to CO2 water vapor, carbon monoxide, sodium, potassium, and sulfur dioxide. The detection of this last compound has highlighted a photochemical phenomenon observed for the first time on an exoplanet. The James Webb Telescope is not the only one to be promising. The extremely large telescope of ESO, the European Southern Observatory, should be completed and put into service in 2028. This telescope, currently under construction in the Atacama Desert in Chile, will be the largest ground-based telescope ever built, with a main mirror 39 meters in diameter. For comparison, the James Webb Telescope orbiting the Sun, 1.5 million kilometers or 930,000 miles from Earth, has a mirror 6.5 meters or 21 feet in diameter. The European Southern Observatory's Very Large Telescope has already demonstrated its capabilities by discovering barium in the atmosphere of the exoplanets WASP-76b and WASP-121b in October 2022. The heaviest element ever found in the atmosphere of an exoplanet. So, imagine what the ELT's capabilities will be. This super powerful telescope, when completed, will stand 3,000 meters or 10,000 feet above the Earth and will capture 100 million times more light than the human eye. We are coming to the end of this journey in the Wolf 1061 planetary system. Now you know that in the universe there are many rocky planets and many multi-planetary systems like ours. If astronomers have not yet found a second solar system, they do not lose hope that one day they will find a planet on which life would abound. Wolf 1061c is a promising exoplanet, which has the advantage of being very close to us. The new telescopes, first the James Webb and then the ELT, will be able to tell us more about this exoplanet, its characteristics, whether it is suitable for life, and above all, perhaps one day, answer the question that everyone is asking. What does life look like 14 light years away from our planet?